In the previous video, we took a look at what happens when we try to take and use those properties of inverse functions with the original trig function, but we have different functions, okay? So one's like a cos and one's like an arc sine. And so what if we did that with regular rational or irrational numbers, but what if we did that with algebraic expressions? Sometimes what we could do is we could turn the trigonometric statement into an algebraic statement, okay? And that's helpful a lot in a lot of times, especially for those of you that have to go up through calculus. A lot of times in calculus too, we use this technique. So let's say we want to find the sine of the arc cos of 2x. Now, remember in the previous video, what we did was we started by letting theta be equal to the arc cos of whatever was inside. Okay, so theta was equal to whatever that inverse trigonometric function was. And by property of inverse function, that's the same as saying the cos of theta is equal to 2x, right? Or the cos of theta is 2x over 1. And remember that the cosine is the adjacent over the hypotenuse. So that means we can make a triangle out of this. Okay. And if this is theta, the adjacent is 2x, the hypotenuse is 1. And so for us to solve this, we could use the Pythagorean theorem to find the missing third side. Right? So let's call that b. Okay? And so we would say that 2x quantity square plus b square equals, or I'm sorry, plus b square is equal to 1 square. All right? Or if we square out that 2x, that's going to say 4x squared plus b squared equals 1. To solve for b squared, we subtract 4x squared from both sides. So we get that b squared equals 1 minus 4x squared. And then finally, we just take the square root of both sides, 1 minus 4x squared. All right. So the reason we have this is so that way now what we can do is just substitute back in, okay, for theta, okay? So we're going to replace arc cos with theta. So really we're looking for the sine of theta, remembering that the sine is the opposite over the hypotenuse, okay? And that's the same thing as our newly found 1 minus 4x squared under the square root. And then the hypotenuse is 1. And so we could really just say that this is 1 minus 4x squared. So notice that that's purely an algebraic statement, okay? There's no trigonometry involved in that any longer, okay? And there are benefits to that, okay? A lot of times trigonometric functions are transcendental, meaning that they're based on a lot more complex sort of definitions. Algebraic is basically just plug it in and evaluate. This one we have the cosecant of the arctangent of x over 3. And so once again, I'm going to set theta equal to the arctangent of x over 3. And by our definition of inverse function, that really means that the tangent of theta is going to be equal to x over 3. Remember, the tangent is going to be opposite over the adjacent. And so if we construct our triangle, the opposite side is x, the adjacent side is 3. Let's call this c for the hypotenuse. And so that means by Pythagorean theorem, x squared plus 3 squared equals c squared. Or x squared plus 9 equals c squared. And then if we took the square root of both sides, we would get that the square root of x squared plus 9 equals c, right? And again, technically it's a plus or minus root of x squared plus 9, but we're just worried about the domains of positive values. Okay. Now, this becomes the cosecant of theta. Okay. Remember that cosecant is the reciprocal of sine. Okay, so we know that the sine of theta is the opposite over the hypotenuse. And so the cosecant is going to be the hypotenuse divided by the opposite, okay? And in this case, the hypotenuse is this square root of x squared plus 9. And the opposite is x. Okay. And this would be the algebraic expression that replaces this trigonometric expression. Okay. Unfortunately, there's no easy way to check this on a graphing calculator. Okay, so for us, what we just have to do is we just have to trust the fact that we're good with our trigonometry, our inverse trigonometrics, and our Pythagorean theorem. Okay, so that's everything for inverse functions in this section. Okay, so the last section we're going to be looking at in section 4 is going to be our applications of trigonometry.